Hi, everybody. I'm Chaz Murray. I'm going to talk to you about human-AI partnerships in education at scale. I'm going to emphasize an industry perspective as perhaps the most unique contribution I can make to this bunch. And I'm not going to assume knowledge of the domain, so I'll explain some things that a lot of you already know, and hopefully I'll provide a few tidbits that you may not know. First, about me and my time at ISP. My PhD advisor was Kurt Van Lane. And I'm deeply grateful to Kurt and glad to know him, as with so many of you, both the faculty and the alumni. Kurt took me from the underwater goofball you see on the left to PhD on the right, albeit with a lot more gray hair. My dissertation topic was an evaluation of decision theoretic tutorial action selection, which is using a dynamic decision network to decide what a computer should do given multiple competing goals. I'm a cognitive scientist with Carnegie Learning. We're a commercial spinoff from Carnegie Mellon, and we maintain strong research ties. That's an important, good part of my job, including with some of the people here in this room. Our core technology is the cognitive tutor, which is our intelligent tutoring systems that grew out of the Andersonian ACT-R cognitive theory. We do mainly math for grade levels 6 through 12, plus we're doing some college, and we're doing branching out into computer science. I've even done some grammar tutors. We're in about 1,400 schools currently, and we have about 500,000 students, active students a year. Speaking of Carnegie Learning, I'm missing today, Bill Peduto was visiting Carnegie Learning with River, the Pittsburgh ambassador dog, canine ambassador. And so, hi from Carnegie Learning. That's actually the mayoral office, not Carnegie Learning's offices. These tutors have been shown to be effective. They're a real-world success story for the kind of work we do at the Intelligent Systems Program. There's been a lot of studies about them, and most commonly cited nowadays is a RAND study published in 2013 that showed that in the second year of implementation, students using the cognitive tutor learned about twice as much as the control group. I want to talk a little bit about the AI involved, and there's a couple of core technologies that cognitive tutors are well known for. The first of these is model tracing. The tutor can automatically do all the problem steps along a reasonable solution path that a student would take. The diagram to the left, to your left there, is automatically created problem solution graph for a particular inequality. Given that, we can trace the student's path through that solution space, and we're able to provide step-specific guidance wherever they may happen to be. The other core AI technology is knowledge tracing. For that, we use a dynamic Bayesian network. We use a Bayesian network to reason from the student's knowledge to the student's knowledge, which is not directly observable, based on observable student actions. We use a dynamic network because the student's knowledge changes over time. That's the point of tutoring. With the traditional knowledge tracing paradigm, there's a probability increase in that the student knows the relevant rule if they get a related step right, and a decrease, one single amount of decrease if they get that step wrong or if they ask for any kind of help. A Carnegie Learning extension, which I implemented this, we adjust the probability of knowledge corresponding to the level of help they receive. For instance, if they receive a goal-setting hint just tells them which step to do next in that big graph you saw without telling them anything about how to do it. If they get one of those and do a correct action, then there's a relatively high probability that they actually do know that step. So there's a small decrease in probability that they know the rule. If they require a teaching hint, which teaches the relevant rule in the context of the problem step, then there's a lower probability that they already knew that rule. And so there's a larger decrease in the probability. And if they require a bottom-out hint, which tells the student exactly what to enter so that they don't get stuck, or if they make an error, there's the largest corresponding decrease in the probability that they know the rule. With knowledge tracing in hand, we can perform mastery learning. Rather than present a fixed problem set, we present problems until the probability that the student has reached mastery on each of the rules in the target domain is above threshold, typically 95%. And we can also present problems that target the student's unmastered skills for efficient learning. We have to do all these things at scale. I already mentioned we have about 500,000 students. Someone just told me we've had about 1 billion tutoring transactions so far this academic year. We have to provide math curricula for grades 6 through 12 plus tutors and textbooks. And so some of the technologies we use, we have an SDK to develop cognitive tutors for types of problems rather than a problem at a time. Given that, we use constraint-based problem generation to generate hundreds of problems, problem variations per problem type. We're in the midst of translation to other languages. We've designed this so we can translate to lots of languages as opposed to designing for just one. Currently we're doing Spanish, but there are others likely coming up. And to do that, we've had to generalize our language processing. And just one example thing is that we've had to segregate our language-specific text so that non-technical translators can do their work independently. It's hard to get ISP people who are also bilingual or in whatever language you happen to need. One of the other things we had to do at scale was create worked examples. Worked examples have been shown to be effective, for instance, interleaved with problem solving. Well, we have a lot of tutoring content for which we need worked examples. To do that, what we do is we play our cognitive tutor in autoplay, step-by-step mode. We present the first step to the student along with the teaching hint and give the student a chance to enter the correct response. If they're successful, great. If they fail, we give them the bottom-out hint and give them another chance. If they fail again, then we automatically complete the step for the student and move on to the next step. By the end, the student has been engaged in creating a step-by-step work example that they can refer back to later, and with a little breadcrumbs they can click on to see the help that's available for each step. We also have lots of dashboard and database tools to monitor tutor and student performance at various grain sizes, from grade level down to the specific problem step. To the left there is from our previous version dashboard, a display for a particular step within a particular problem. And we can also, when we need to do this, replay any student's steps on a particular problem so we can see, for instance, if the cognitive tutor goes wrong, what might have happened, or see what trouble students may be having. One of the things that our dashboard displays is segmented learning curves. To explain those, I've got a standard learning curve on the left. Along the x-axis is opportunities to practice a skill. Along the y-axis is the percentage of students who get that skill correct. We want students to learn, and so we expect the curve to rise from left to right. But the blue curve here is the learning curve, and it doesn't rise. It hovers around 30 to 40% before it gets really wacky over at the right side. The key to understanding this is the red curve, which shows the student population. With mastery learning, students drop out of the population as they master that workspace and move on to something else, so that by the end, by the 20th opportunity, there may be one student left. If that student gets it right, then it's 100% of the students got it right. If they get it wrong at the 23rd attempt, then 0% got it right. So to make sense of what's the learning that's going on with a shifting student population, we divide the learning curve into the population into cohorts of students who achieve mastery in different numbers of learning attempts. That's the segmented learning curve on the right. And that shows that most of the students, most of the cohorts, in which is most of the students, do achieve mastery. It's the students who are achieving mastery more slowly, or those who never achieve mastery, that are making the learning curve look so screwy. But what we do isn't just AI, and I have so much to tell you about this, but I have limited time, so I'm going to focus on just one aspect. And a key here to this is this quote from Herb Simon: learning results from what the student does and thinks, and only from what the student does and thinks. The teacher can advance learning only by influencing what the student does to learn. The cognitive tutor is successful only in partnership with the student to the extent that it elicits learning in the student. More generally, in the classroom, there's a human-AI partnership, as Vincent was mentioning, between the student and the cognitive tutor. The student learns from the cognitive tutor, and I should have mentioned that the cognitive tutor learns about students from observing them and all this data we have. Between the student and the teacher, of course, the student learns from the teacher and gets help beyond what the cognitive tutor can provide. And also the teacher teaches and provides access to learning resources. And there's a partnership between the tutor and the teacher and the cognitive tutor as well. The teacher uses the tutor as a teaching aid and homework helper, and the cognitive tutor provides information to the teacher about individual students in the classroom as a whole. And looking to the future, I don't know how much time I have left. 1 minute. Okay, so I'll tell you a few things about that. We haven't focused enough on effective and metacognitive modeling and adaptation. It's been all the rage the last 10 years or so. The cognitive tutor focuses on cognitive modeling and adaptation, but we need to do more with this. And so far we do it, but we do it implicitly. With mastery learning, we can replace some tests with continuous assessment. If we know the student has mastered the material, there's no need to take time out from learning to take a test. With rising expectations in technology, more immersive interfaces, and particularly with natural language processing improvements, which I'm loving, conversational interfaces, and Pam Jordan, Patty Albacete will be talking to you about that. And more generally, learning outside of school settings. To do that, we need to provide integrated text, problem-solving videos. If there's something we don't have that the student needs, we need to be able to refer the student to all the resources that are available online these days. And just in general, a trend towards, and someone else mentioned this, towards specific credentials to do the task you need to do, such as a job, and less emphasis on general education. So, any questions, anything I glossed over, I'd be glad to get into if you want to talk. Yes, Peter?
It's interesting to know that you try to do mastery learning next problem selection adaptively. In fact, it's frequently declared but rarely happens. Typically, it's going through the same sequence. So how are you adapting the next problem in the mastery learning sequence to the student's skills? Any hints? Any specific principles?
Yeah, as a matter of fact, I simplified that a little bit when I described it. There are several considerations in choosing which problem to select next, and we typically actually do it in 3 phases. First of all, we try never to repeat a problem scenario. Although we may have 100, 200, typically we have 200 problem variations for a problem type, and there'll maybe be 15 or 20 scenarios. We try not to repeat that scenario. That's one of the principles. The other principle is we try to try to hit different skills at different problems. So in our learning phase, in the first phase, the early phase, we try to give them usually try to give them a broad perspective on it. In the intermediate phase, we present them with more challenging problems. And at the final phase, we try to focus on the problems that address the skills that they haven't mastered yet. We actually have more than one remediation, we call it remediation, our plan to what to present to the student, but that's the most common. Okay, any hardballs, or I can save some time and move it on? Yes.
I studied alchemist with my kids when he was young, from art of problem solving. Are you familiar with alchemist?
No, I'm not familiar with alchemists.
So I wanted to make a comparison. That's fine. So they had the same thing, but the problem was it is so opaque that you don't see what happens in the background. So it gives you a problem based on what you solve and what you cannot solve. The next problem is big for you, but we don't know how it is done. And
You don't know why.
mastery is really there or not.
Yes, and there's a lot of people believe in, there's a movement for open student models, so the students can inspect their own model and see what's going on. And that relates to just general modeling over a lifetime, for instance. There's a whole lot that can be done with the modeling, but the opaque versus not opaque is one of the dimensions. Okay, I'm going to move on and let the next person talk.